All right, just confirming that everybody can see my screen.
Yes.
Okay, so my name is Jade. If you know anything about me, I love talking about vectors. So that's what I'm going to be talking about today. So what do I mean when I say a vector? Um, and vector is such an overloaded term in computer science. And I'm not talking about any of these actually. What I'm talking about is SIMD, single instruction, multiple data. So what is SIMD? SIMD, or vector programming, is using the hardware units built into your CPU to process data in a single thread. This is also sometimes called instruction level parallelism. And why would you want to do this? Well, the hardware is already in your computer. You might as well use it and get more parallelism and more speed. But most of the time, you really don't need to know about it or use it explicitly. Compilers are awesome and give you free performance. Um, so that's the end of the talk, right? We're done. Thank you all very much. Have a nice day. Uh, I'm kidding. Um, that's not the end of the story here. Because what happens when the compiler doesn't do it for us? This can happen when the compiler doesn't know it's safe, especially when dealing with floating point, or maybe we just wrote our code really badly. And maybe not badly, but it's easy for a human to understand, but it's really bad for SIMD or any other reason. And in Chapel, this is kind of where the story stopped for a while. If the compiler can't do it for you, well, you're just kind of out of luck. And so this is, in my view, Chapel's missing piece. Chapel has this multi-resolution philosophy. You have high-level features and low-level features, and all the high-level features are implemented in terms of the low-level features. This is awesome for multi-core and distributed parallelism. You can write this cool forall loop, and this is going to invoke a parallel iterator and give you distributed parallel performance. But if that's not enough, you can go in under the hood and rewrite all that same kind of magic into your own explicit loop, um, and use lower level features to get the same effect. But what about instruction level parallelism? If I write a for each loop and it fails to vectorize, what do I do? Uh, Nothing. Right now, you're kind of out of luck without, writing assembly or C code. So what is my goal here? I want to be able to write explicit vector code. I don't want to write C or assembly. And this is Chapel. I want it to be portable. And I also want it to work with all of the other Chapel features. So it should work seamlessly with arrays and distributed arrays and tuples and all that good stuff. And of course, it should be fast. And lastly, I don't want to have to maintain this thing all the time. And I want it to look somewhat nice. So I introduce CVL, which is Chapel Vector Library. Um, and it's got all kinds of cool stuff. There's this new portable vector type that maps down to the actual hardware. It's portable on both x86 and ARM, and it supports all your common vector operations you might expect, from math to memory operations, and shuffles and permutations and blends, which in my opinion is the big workhorse of vectorization. There's also some support for trigonometry, and most importantly, it integrates seamlessly with Chapel, written mostly in pure Chapel code, and it works both in parallel and distributed. And of course, it's open source. I'll have this link to the repo at the end of the talk as well. But this is all just high level description. Let's see some examples. So many of you have probably seen this program before. This is called Stream or Saxby or Daxby. And essentially, I'm taking two vectors, which is x and y. I'm adding them together, but I'm also going to scale x by a scalar amount, which is a, and put them in a third vector, z. And I can express this computation in Chapel very succinctly. This is both distributed and parallel. What's the same thing look like with CVL? So here's one example of that program written in CVL. I'll call out a couple things on this slide. First of all, I'm specifying the exact size of the vector that I want. It must match the hardware type. I'm going to turn that scalar value that we have, A, into AV, which is a vector. So this is now in a SIMD register. And then I'm going to adjust my loop iterations. So instead of operating explicitly on every single element in the array, I'm going to do every fourth iteration because each iteration of the loop is going to handle 4 values. And then I have a whole bunch of memory operations to load and store the memory explicitly. But this all kind of hides my computation. So it's explicit, it's distributed parallel, great, but it's a little over verbose. So let's do a little better. Here's the better version. So as you can see with the better version, I've kind of gotten rid of a lot of the boilerplate and I've replaced them with these iterators. These are parallel distributed iterators, and they handle all the load and store logic and let the computation kind of shine through the clutter. And that scalar no longer has to be explicitly made into a vector. It's automatically done by the library. And just to kind of compare it back to that original stream, you can see it's very, very similar, but without kind of all the extra, or with explicit vector optimizations. So is this better? No. With default rectangular arrays, it's identical performance. So you're doing just as good as the compiler is going to do for you. And at distributed scales, it's actually slower. And I have a lot of theories about this. I haven't actually, dug into those theories yet. I basically put this together for these slides and haven't dug into it. These are all things that can absolutely be closed and made better. But all of this is to say, just because you can write something with its explicit vectors, it doesn't mean you should. So something simple like this doesn't really benefit from explicit vectors. So let's see something that does benefit from explicit vectors. This is a very brief snippet of a k-means clustering algorithm. If you aren't familiar with what k-means clustering is, I have a whole bunch of points, and I want to find out which ones are close together in little clusters. And just a brief look at what this code is doing. Basically, I have a bunch of centroids, which is the center of the cluster. I'm going to compute the distance between my current point and that centroid. And if that is the new minimum distance, I'll update that minimum. And so this is expressed fairly concisely in Chapel, but it's maybe not the most performant. And I want performance. So I'm going to write some vector code for it. And the vector code is a lot more verbose, and this is only a small section of maybe a couple hundred lines of Chapel. But you could still see this same kernel in there. There's the compute the distance. The call looks very similar. I'm calling my distance function. And then instead of conditionally updating the minimum, I'm going to determine which value to use with this bit mask and these bit selects. So that way, I'm always updating the minimum value to either the previous value or the new value. And this is to avoid those branches and use more vector optimization operations. So this is cool. This is great. Is it faster? Yes. At small problem sizes, it's not that better. It's about the same. But as you scale up the problem size, you start seeing the effect of the explicit vector codes. So this is awesome. This is great. What's the catch? Well, for CVL, there's no catch. But as far as getting this performance, you have to write your code differently. Both programs, the Chapel and the Chapel plus CVL, are using the data structure on the left. And I've structured my data so X and Y are separate. They're in contiguous memory together, and vectors can run across them really easily. If you write with the right data structure, it's easier for a human to understand and easier for a human to read. But the plain Chapel code is going to be slower, and it's much harder to write a vectorized version. It just takes more mental load and more operations, and your code will be slower. So data is important. So that's a cool benchmark. How does this all work? Is this just magic that I wave my magic wand? No. This is built with many layers of abstractions. So there's the top level vector type, and that converts into a lower level implementation type. And that implementation type gets implemented for every architecture, every bit width, and I've basically stamped out every operation. So each implementation type has those operations, and I've defined a set of behaviors that it must conform to. This is how you get portability. We wrap the underlying operations so that you get consistent behavior across platforms. And part of that means you can't do arbitrary shuffles and permutations just by the way that SIMD architectures are put together. And at the lowest level, each of these operations is either calling a compiler intrinsic, which is essentially just calling the assembly instruction, or it's some C wrapper code that I put around that compiler intrinsic for portability. And that's so what I mean by, this is a Chapel-ish library. And I think this is a fantastic example of Chapel metaprogramming. All of this, abstraction, it's all done at compile time. So by the time you get assembly code, everything, all of this boilerplate is gone. And you're just left with the explicit vector operations, which means you have good performance, and you also give the compiler the chance to build on top of your smarts and make your code even faster. This is great. I've got a couple more performance comparisons, and then we should have time for questions, which I think there's already one in chat. So this benchmark is from the computer language benchmark game. It's an n-body benchmark. It's basically got a bunch of planets, and it's simulating their movement through the solar system. I'll give the caveat right now. The only version of this that I wrote two versions is the Chapel Plus I got from the language benchmarks games, and I ran them on a variety of hardware. I ran them on my laptop and two different Linux systems that I have access to. And I'll just highlight the winning ones basically. And on ARM, Chapel actually, just plain Chapel is best. For one specific platform, which is what the computer language benchmark game is like written for, C wins out because it's written in what is essentially assembly. And then yay, Chapel plus CVL on a bigger machine is the clear winner here. So yay, Chapel's the best at vectorization. Kinda. I mean, as you can see, this is very architecture dependent. And actually, hand-coded C can be much faster, but it's not portably fast. So, it was fast on one particular architecture, and I couldn't even run it on an ARM computer. So yay, win for Chapel. And this is the benchmark that I wrote entirely myself. And it's converting RGB images to grayscale images using integers. And this problem size is scaled per platform. So I did different problem sizes based on the memory of the machine. And by far and away, you can see that using explicit vector optimizations absolutely outstrips the Chapel compiler and does a much, much better job of getting performance. You can also write this with floating point, and you see pretty much the same effect. And again, yeah, it's faster, yay, performance. So yes, writing explicit vector code is absolutely faster and can be worth it. Both this benchmark and the previous benchmark are available in the GitHub repo if you want to go look at them. I hope they're readable. If they're not, I didn't do a very good job writing this library. So in conclusion, CVL lets programmers fill a missing gap in Chapel's parallel story. It lets you write explicit, portable, and performant vector code. And I think it's pretty and easy to read. And it's totally ready to use. It's up on GitHub. I have it fully tested across a whole bunch of configurations. And the last thing I want to end with here is this is not a silver bullet for getting good performance in Chapel. You shouldn't go out, start using this library, and expect your code to magically get faster. It can help performance, but it's not the silver bullet, and it's just another tool in the toolbox for when the auto-vectorization fails you. And I have a whole bunch of things that I'd like to keep working on in this library. I tease kind of the vectors ref, which automatically does some stuff behind the scenes for you. It's got kind of limited support right now. And kind of the white lie that I told through this whole presentation was about tail loops. So what happens when your data doesn't perfectly fit the vector? You can handle that today. It's somewhat more manual. So, how do you get a slightly better story for those kinds of loops? And it is possible to have more flexible shuffles. I know I talked about the hardware, but compilers are magical things, and we can get more flexible shuffles if we can leverage the compiler a bit more. And there's already tight integration with Chapel types, but there's always more that can be done there. That is all I have for you all. Thank you all very much, and I'm happy to take any questions.
Great. Let's thank the speaker with a virtual round of applause. Are there any questions from the audience? Yeah, Michael.
Hey Jade, thanks for the talk. I have two questions. First question is, with your grayscale example, what was the width of the integers you were using? Were they 8-bit?
It was scaling 32-bit integers down to 8-bit, doing the math at 8-bit, and then outputting the 8 bits.
Okay, and are you seeing are the sort of number of integers per register making sense with the multiples of improvements you're getting? Like, yeah, okay, great.
Yes.
I couldn't do the figuring in my head without the other number. Other question was, do you have any thoughts on how it can work with the ARM SVE, where notionally the vector size might not be fixed in the architecture? Maybe it's fixed in, in practice now, I don't know. But any thoughts there?
That is something I haven't quite explored yet. I think it could fit really well into this ecosystem. And the compiler should know beforehand about the architecture, maybe not, the exact bit width, which is not baked into the hardware. But I think that this can map to that nicely. And the way that I've set this up, the ARM is just the ARM Neon is just one backend, and you could totally write a new backend for SVE.
Oh, okay. So you don't have it working with SVE yet.
I do not know.
Is the sort of the thing that wasn't the answer to the question I didn't ask.
Yeah,
Anyway,
no,
thanks
it
a
doesn't.
lot.
Yep, thank you.
Then we have a question in the chat. On slide 17, why is the relative performance gap at 100 million points not as good as at 10 million points? And second question, do you expect to do tests on ARM SVE?
So basically, I didn't investigate this performance that much. I kind of tested it at some lower scales, the 1 million and 10 million, and just for fun, decided to throw in 100 million for this talk. So I haven't investigated, why is it this scale of, it's hitting some sort of bottleneck. It's possible that the compiler is doing a better job of vectorizing at the bigger scale. I don't know. It's definitely something I want to look into. And to address the SVE question, doesn't work with SVE yet, partly because I don't have access to a machine where I can test with SVE. But yeah.
And there's another question in the chat. For the n-body benchmark, does the performance become better for the larger number of particles?
I didn't test it at a larger, honestly, didn't test it at a larger number of particles because the computer language benchmark game only uses that size. So I just use that size as well.
Cool. Okay, we have 1 minute, so maybe let's take the last question in the chat. Is extending CVL to support 512-bit vectors more complicated than the current implementation?
It won't be any more complicated than this current implementation. You basically just add another backend for x86 512-bit vectors. I currently cap this at AVX2 because that's the most widely available vector set. And I'm not sure how committed Intel or AMD are to AVX 512 in the long term. So we'll see.